My name is Abhishek Madan, and I will be presenting Visualizing Query Traversals over Bounding Volume Hierarchies using Treemaps. This is joint work with Nobre at the University of Toronto. So what are bounding volume hierarchies? Let's first take a look at an example scenario that comes up frequently in computer graphics applications like ray tracing. Suppose I have a triangle mesh that looks something like this, where I have several triangles glued together into some shape, and I want to answer the following question. What's the closest triangle to my starting point along a given direction? This is typically called a ray intersection query. The simplest way to do this is to loop through the entire mesh to find the closest triangle that intersects this ray, but of course this scales linearly and is much too slow. Spatial tree data structures are used to speed these queries up, and that's where bounding volume hierarchies, or BVHs, come in. As the name implies, we split up the entire mesh into progressively smaller pieces, enclosed by geometrically simple bounding volumes, to form a hierarchy of clusters. Intersecting rays with the cluster's bounding volumes to quickly eliminate swaths of candidate triangles makes the query much faster than a full linear search. However, despite their usefulness, it's very difficult to understand and visualize what goes on in an individual VVH query, and answer questions like, which nodes are visited, and in what order are they visited? Why is this difficult? Consider an image rendered of the ray tracing. For each of the millions of pixels in a high-resolution image, we need to send out a ray from the camera to a point on an image plane, and then traverse a tree with thousands of internal and leaf nodes on even moderately sized geometry. Even if we consider extremely low-resolution images, like 20 by 20 images, we still have hundreds of queries with thousands of tree nodes to potentially interact with, leaving us with far too much data to show at once. On top of this, even displaying trees is hard, since just drawing the bounding volumes on top of the original geometry creates clutter. Our solution is to combine a 3D viewport showing the geometry with a tree map, a visualization technique that can compactly display abstract tree data. In the viewport, the mesh can be rotated around to view it from any angle, which is crucial when viewing 3D data. Also, hovering over a node in the tree map highlights the corresponding portion of the mesh in the viewport, providing correspondences between the two views without causing visual clutter. Only a small portion of the tree is shown at a time, so even very large meshes can be shown efficiently. Clicking on a node zooms into the subtree corresponding to that node, which makes it easy to navigate through the tree. The highlighted regions at this lower level are smaller, but we can still access the root of the current view with the top node. Clicking on this top node zooms us back out. To view ray intersection queries, a user can click on a pixel in the pixel grid, each of which represent a ray sent out from the camera and onto an image plane. One of two sequential color maps is applied to each pixel based on whether the ray hit or missed the mesh, and how much work is done by the query, measured in terms of leaves visited. Green pixels represent hits, and orange pixels represent misses. Also, lighter colors represent less work, while darker colors represent more work. Scale showing the amount of work done for each type of query result are shown in the color bars below the pixel grid. With all this information, users know which pixels represent the most expensive queries that need a closer look. Let's view a query now. Clicking on a pixel reveals the query in both the tree map and the viewport. Highlighting and viewport navigation work just like before, but now we can see the nodes involved in the query as they are highlighted with the blue sequential color map. Unlike with the hit and miss color maps, this one encodes the query's traversal order, with lighter colors being visited earlier and darker colors being visited later. This way, we can see the order of the traversal. The text labels give more precise breakdowns of traversal order by showing the intervals of visited leaves. Also, if the intersection returned a hit, the node containing the intersecting triangle and the triangle itself are both outlined. This lets us see the point in the traversal where the final result was located and how much additional effort was needed to eliminate other candidates. Zooming in and out also works like before, where zooming in shows the nodes visited within the parent that was clicked on and a smaller triangle group in the viewport. If we were to zoom in all the way down to the leaves of the BVH, we would see the individual triangles that were visited. Now that we have seen how this visualization works, let's apply it to a different example and see how it identifies flaws in a very naive starting BVH implementation. We're viewing a query pixel aimed at the middle of the trunk. We can see through the number of visited nodes in the tree map route, as well as the number of non-purple tree map nodes, that this query visits nearly 1,200 leaves of the BVH. The color bar at the bottom, and the colors in the pixel grid, show us that the query we picked isn't a pathological example either. Many pixels are dark green or orange, and those queries visit several hundred and sometimes well over 1,000 leaves. Turning our attention towards the geometry, We see that we are visiting several unnecessary parts of the mesh. We only need to visit the near side front doors and windows of the truck, but this traversal also visits the rear and far sides of the truck. Let's try to change our traversal strategy to skip unnecessary regions. Our basic implementation only uses the bounding boxes to check for the existence of possible intersections, and if an intersection is possible, the traversal will examine both children depth first in an arbitrary order. However, it's not necessary to visit both children or to visit the children in an arbitrary order. For example, look at the two blue nodes at the bottom of the tree map, which are siblings in the BVH. Rather than traversing both children, we could skip the lighter node if we find an intersection in the darker node, since we know it's farther away from the ray and will be occluded by the darker node. We can't make that decision in this particular query, since the hit location is in another node in the top right of the tree map, but we could at least facilitate our traversal to try to make this optimization by ordering the traversal of those two nodes. The colors and interval labels show that the closer node is visited later in the traversal, so we could instead swap the order these nodes are traversed. Adding this ordered traversal implementation, the visualization changes. We can see that the cost of this query has gone down by almost 500 leaf hits, from nearly 1,200 to about 700. This is primarily due to no longer visiting the node at the back of the truck. We also did swap the traversal order of the nodes at the front of the truck, though in this particular query, the swap did not change performance. Furthermore, the maximum query cost has also gone down to roughly 900, though we still have many queries near that maximum. However, there is still a big problem here, and it's related to the structure of the tree itself. The two subtrees in the middle of the truck are entangled together in a way that prevents a smart traversal from separating the two. This is due to our original builder using a simple partitioning strategy, based on the position of the triangle barycenters relative to a split plane along the longest axis of the box. We will use a tree builder based on the surface area heuristic to pick a better plane at each internal node that will avoid such behavior. For more details, see the original surface area heuristic paper by McDonald and Booth, and our paper for details on our specific implementation. With a surface area heuristic-based tree builder, the visualization changes yet again. We see drastic improvements in query costs for the selected query and in max query costs over the entire image. Qualitatively, we can see that we only need to visit a single internal node visible at this level, which happens to be well aligned with the image plane. It's worth noting that we see a particularly drastic improvement because the original implementation is very naive, and the surface area heuristic builder happens to work particularly well for this setup, so performance improvements will vary for different meshes and camera positions. To summarize, we presented a visualization technique for viewing BVHs and ray intersection queries, which relies on separating geometric and structural information to reduce visual clutter. These views are connected through highlighting, so correspondences can be viewed on demand, and users can zoom in and out of tree nodes for scalability. Users can view aggregate performance of a set of ray intersection queries from a pixel grid, and individual query traversal traces by selecting individual pixels. We believe this technique will be useful to students, practitioners, and researchers who want to understand BVH building and traversal implementations in more detail and analyze their performance. Thank you for listening.